Welcome tonight. The journey begins at the edge of human reach, where an aging spacecraft from the 1970s still whispers to Earth from interstellar darkness more than 15 billion miles away. This is the story of Voyager 1, of faint radio signals, crossing impossible distance of NASA's careful fight to keep an old machine alive, of shrinking nuclear power remote repairs across the void, and the long path from Jupiter and Saturn to the boundary between the solar system and the stars. In this quiet documentary, the vastness of space meets the patience of science, and every weak transmission becomes a sign of endurance. Before settling in, please take a moment to like the video, subscribe to the channel, and turn on notifications so more calm space documentaries like this can continue to arrive. Now the signal grows faint, the darkness deepens, and Voyager 1 continues onward. Far beyond the bright lanes of the major planets, beyond the broad orbit of Neptune, beyond the scattered icy bodies that still circle under the sun's rule. Voyager 1 moves through a region where space is no longer shaped in the same way by the flowing breath of the solar system. It travels in interstellar space, the thin material between the stars, carrying a working radio system that still reaches Earth across a separation greater than 15 billion miles. That fact is simple to say and difficult to hold in the mind. The spacecraft itself is not large. Its main body is about the size of a small room. Its dish is wide but modest when set against the scale of the distance it crosses with every transmission. Around it, there is no glowing highway, no visible thread linking craft and planet, no corridor built for communication. There is only darkness scattered with atoms, charged particles, magnetic fields, and the slow drift of dust. Yet in that darkness, a signal continues to leave a machine built in the 1970s and continues to arrive at Earth as a real measurable trace. The signal is weak beyond ordinary intuition. By the time it reaches Earth, the radio energy spread across space has become so faint that it must be treated less like a strong beam and more like a fragile pattern hidden deep within background noise. Even so, it remains enough. That is the first essential reality of Voyager 1. Its contact with Earth does not depend on power in the everyday sense of force or brightness. It depends on patience, precision, and the strange reliability of physics acting across immense emptiness. The spacecraft transmits, Earth listens, and the exchange persists, because radio waves do not need air wires or any physical bridge beyond the laws that govern electromagnetic radiation. In the space around Voyager 1, the environment is almost empty by human standards, but not truly empty. Interstellar space contains a very thin gas, mostly hydrogen, with traces of heavier elements, along with energetic particles, moving through magnetic structures that stretch across the galaxy. Compared with the denser environment closer to the Sun, this region is sparse and cold, a place where the nearest stars remain vastly distant, and where sunlight, though still present, has faded to a hard and distant gleam. The Sun is no longer the commanding center it appears to be from Earth. From Voyager 1, it has the status of a bright star among other stars still dominant in one direction, but no longer the surrounding sky. This change in environment gives the mission part of its meaning. Voyager 1 is not merely far away. It has crossed from one broad domain into another. It has moved outward through the planetary system, outward through the outer layers of solar influence, and into a medium that belongs to the galaxy more than to the Sun. Even so, the spacecraft remains linked to its origin by timing, geometry, and memory. Every command it receives begins on Earth. Every report it returns is a delayed sign that the craft continues to function. This continuing contact gives distance a practical form. Distance is not only a number of miles or kilometers. It becomes waiting time, uncertainty, beam width, receiver sensitivity, and careful mission planning. It becomes the reason no action is immediate and no correction can be casual. When engineers work with Voyager 1, they work across a gulf so large that even light, the fastest known messenger in nature, takes many hours to make the trip in one direction. The spacecraft therefore occupies a peculiar condition. It is still part of human activity, still under guidance, still producing scientific information, yet it also exists in a setting so remote that it behaves almost like an independent outpost. It cannot be handled directly. It cannot be repaired by touch. Its health must be inferred from coded data. Its problems must be solved by reasoning simulation and long-delay command sequences sent into the dark. The emotional force of the mission often comes from this contrast. The machine is old, distant, and weak in power, but it remains legible. It continues to speak in numbers that reveal temperatures, voltages, instrument states, and measurements of particles and fields. The message is not rich in volume. It is rich in persistence. That persistence rests on a chain of unlikely continuities. The hardware survives decades of radiation, cold, and aging. The power source continues to produce electricity, though less each year. The radio system continues to function. Earth continues to maintain the giant listening systems needed to detect the faint transmission. Teams of specialists continue to understand the craft's design well enough to interpret its behavior and adapt its operation. None of these conditions is infinite, and all of them become more difficult with time. Yet together, they create one of the longest and most delicate technical relationships in human history. Voyager. One therefore stands not only as a probe, but as a demonstration of endurance across scale. A small machine persists in a vast medium. A weak signal crosses a tremendous distance. A human-made object launched during the Cold War still exchanges information with the world that built it, long after the age of its design has passed. Its journey outward makes the solar system feel larger, but its continued contact also makes that largeness feel traversable in a limited and disciplined way. Nothing about the connection is easy. Nothing about it is fast. Everything about it depends on accepting weakness instead of resisting it. The transmission does not overpower distance. It survives distance. In that quiet distinction lies the true character of Voyager 1's communication with Earth. It is not a triumph of volume, but of sensitivity. It is not a conquest of emptiness, but a long accommodation with emptiness. The spacecraft moves on through interstellar space, carrying instruments' memory and a slowly fading electrical life, while Earth continues to receive the whisper it sends home. The immense distance between Earth and Voyager 1 becomes most real when it is measured not only in miles, but in time. A command sent from Earth does not reach the spacecraft at once. It travels outward at the speed of light, which is also the speed of radio waves in space, and it takes many hours to arrive. A reply from Voyager 1 then requires many more hours to return. The full cycle from instruction to response stretches across most of a day, and sometimes more, depending on the spacecraft's exact distance at that moment. This delay shapes every aspect of the mission. It means that no one at Earth can steer the spacecraft in the way a driver steers a car, or even in the way a pilot guides an aircraft. There is no direct touch, no immediate correction, no active conversation. There is only planning transmission, waiting, reception, interpretation, and then another round of waiting. This makes control less like handling a machine and more like setting a careful process in motion and trusting that it unfolds as expected in a distant place. The delay begins with a simple physical fact. Radio communication is not instant. Even though light moves extraordinarily fast, the solar system is so large that the travel time becomes unavoidable. When Voyager 1 was near Earth soon after launch, the delay was brief enough to seem small. As the spacecraft moved past Jupiter, then Saturn, and then the outer frontier of the Sun's influence, the delay grew steadily. The farther the craft traveled, the more the mission changed from active navigation to long-interval supervision. Each hour added to the one-way light time made the spacecraft feel less like a nearby instrument and more like a remote outpost operating by its own prepared rules. Because of that mission, teams cannot respond to sudden changes in real time. If a problem begins on the spacecraft, it may be many hours old by the time engineers first see evidence of it in telemetry. By the time they study the signs, decide on a response, and send a command, many more hours pass before the instruction reaches Voyager 1. Then more hours still pass before confirmation comes back. In ordinary human activity, this would feel impossibly slow. In deep space operations, it becomes normal. The entire craft must therefore be designed around the reality that help from Earth always arrives late. That delay is not merely inconvenient. It is a design principle. It determines how the spacecraft stores instructions, how it protects itself, how it handles faults, and how cautiously engineers build every command sequence. Commands sent to Voyager 1 are not casual messages. They are tightly prepared sets of instructions that must be correct before transmission, because correcting an error is never immediate. A mistaken command may not reveal its effects until half a day or more has passed. If it causes trouble, another long cycle of diagnosis and response begins. This is why mission operations rely on review, verification, simulation, and repetition. Engineers test proposed commands on Earth using software models and careful logic. They examine how those commands interact with the spacecraft's existing state, its power limits, its memory, and its scheduled activities. The act of sending is therefore only the last step in a longer chain of thought. Once the signal leaves Earth, there is nothing to do but wait. Waiting itself becomes technical. Teams know when a command should arrive and when a reply should be expected. They track signal timing precisely. They account for the positions of Earth and spacecraft, for the rotation of Earth, for the motion of antennas, and for the changing geometry of the solar system. In this sense, delay is not vague. It is measured and predictable. Yet its emotional effect remains unusual. The people operating Voyager 1 live in a split time. Their present on Earth corresponds to the spacecraft's past, because the telemetry they receive shows what the probe was doing many hours earlier. When they send commands, they are acting toward the spacecraft's future, instructing a machine that has not yet heard them. The mission therefore unfolds across overlapping layers of time. Earth listens to the past and speaks into the future, while Voyager 1 continues through space in a present of its own. This temporal separation also affects decision-making during anomalies. If telemetry suggests a system has shifted unexpectedly, engineers cannot ask the spacecraft what is wrong in any immediate conversational sense. They must infer the cause from partial evidence. A temperature rise, a voltage change, a computer reset, or unusual data patterns may each point towards several possible explanations. With long delay, the wrong guess carries a real cost in time. One unsuccessful command cycle may consume a day or more. This encourages disciplined thinking. It also rewards a style of engineering that values resilience and simplicity. The spacecraft must be able to continue safely during long intervals when no fresh instruction can reach it. That need helps explain the importance of autonomous routines and fault protection. Voyager 1 is not intelligent in any human sense, but it contains procedures that let it preserve itself when certain conditions appear abnormal. That ability is not a luxury. It is required by lifetime. The mission also changes human expectations of action. Modern technology often creates the feeling that information should be immediate and response should be instant. Voyager 1 refuses that habit. It operates on a scale where slowness is not failure, but reality. The delay does not mean the link is weak in a conceptual sense. It means the link obeys the structure of the universe. Distance imposes time. Time imposes patience. Patience imposes method. Through that chain, the mission acquires its distinctive rhythm. Engineers prepare, transmit, and wait. Telemetry returns, and they study the delayed state of a distant machine that continues faithfully onward. Every successful exchange is therefore more than a technical event. It is proof that a controlled relationship can still exist across a gulf so large that no gesture can cross it quickly. Voyager 1 remains reachable, but only in the deliberate language of long light time, where every message carries both distance and delay within it. The signal that leaves Voyager 1 begins as a carefully generated radio transmission shaped by hardware that is both simple in concept and extraordinary in consequence. On the spacecraft, electrical power is precious limited and slowly declining, so the transmitter cannot rely on brute force. It must send a message that is narrow, stable, and disciplined. That message is carried on radio waves, a form of electromagnetic radiation that moves through empty space at the speed of light. Unlike sound, which requires air or another material medium, radio waves cross the vacuum without needing anything to hold them up. This makes them ideal for deep space communication, but it does not make the task easy. The basic problem is severe. A transmitter on a distant spacecraft releases energy that spreads outward as it travels. Even when that energy is aimed by a dish antenna into a directed beam, the beam still widens with distance. It does not remain pencil-thin forever. Over billions of miles, the transmission covers a vast area, and only a tiny fraction of that energy reaches any receiving antenna on Earth. The weakness of the arriving signal is therefore not caused by damage or interference alone. It is built into the geometry of radiation itself. As the wavefront expands, the same transmitted power is distributed across an ever larger surface. This is why distance punishes communication so strongly. The farther the beam travels, the thinner its energy becomes. Engineers describe this with the inverse square rule, meaning that the received intensity drops in proportion to the square of the distance. If distance doubles, the received strength falls to 1/4. If distance grows by enormous factors, the loss becomes almost beyond imagination. Voyager 1 continues to overcome that loss, not by defeating it, but by working within it. The spacecraft uses a high-gain antenna, the large dish that has become its most recognizable feature. A high-gain antenna is designed to concentrate transmitted energy into a relatively narrow direction instead of allowing it to spread equally in all directions. This concentration does not create energy, but it places more of the available energy where it matters. The dish reflects radio waves in a controlled pattern, sending them outward in a tight beam aimed toward Earth. That beam is still broad on planetary scales, but narrow compared with a fully unfocused transmission. Its usefulness depends on pointing accuracy. Voyager 1 cannot simply send a signal into the general sky and hope it arrives. The spacecraft must orient its dish with great care so the beam continues to include Earth as both bodies move through space. That requirement turns attitude control, the control of spacecraft orientation, into a central part of communication. Small errors in pointing can weaken the signal or even move the main beam away from Earth enough to threaten contact. The transmitter itself produces a radio carrier, a stable wave at a chosen frequency that serves as the foundation for information. Data is added to that carrier by modulation, a controlled alteration of the signal that encodes measurement system state and engineering information. In simple terms, the carrier is the steady tone, and the telemetry is the structured change placed upon it. The process must remain extremely stable because Earth receives not a loud broadcast, but a trace. Any unwanted drift in frequency timing or pointing can make the trace harder to separate from noise. For that reason, deep space communication depends on precision at both ends of the link. Voyager 1 must maintain transmitter health and antenna alignment, while Earth must know where and how to listen. The signal's journey through space is in one sense clean. Interstellar space is not crowded with weather clouds or the dense atmospheric effects found near Earth's surface. But clean does not mean simple. The wave still interacts with the motion of spacecraft and planet. Relative motion changes the observed frequency through the Doppler effect, the same general principle that changes the apparent pitch of a passing siren. As Voyager 1 and Earth move relative to one another, the frequency received on Earth shifts slightly. Engineers predict and track this shift very carefully because accurate reception depends on tuning to the correct place. The signal must also remain coherent enough for detectors on Earth to integrate it over time, gathering evidence of its presence from a background of thermal noise, electronic noise, and natural radio emission. In this setting, every part of the transmission path matters. The spacecraft's power budget matters because the transmitter competes with other systems for limited electricity. The antenna geometry matters because beam shape determines how efficiently energy is directed. The spacecraft's spin and orientation control matter because communication requires stable pointing. The chosen frequency matters because different parts of the radio spectrum behave differently, and because Earth-based systems are designed around particular deep space bands. Even the long history of the spacecraft matters, since aging components and declining power gradually narrow the margin for successful operation. Yet, despite all these constraints, the beam continues to cross an immense darkness and arrive as a detectable whisper. This gives the communication link a special character. It is not spectacular in the ordinary sense. There is no bright flash and no dramatic display. The achievement lies in the disciplined shaping of weakness. A modest transmitter on a remote spacecraft, using careful direction rather than overwhelming power, sends a patterned wave through billions of miles of space. That wave becomes unimaginably faint, but not meaningless. Its structure survives, the carrier survives, the encoded state of the spacecraft survives. Earth then has something real to receive and decode. The beam from Voyager 1 is therefore best understood, not as a shout cast into emptiness, but as a thin and orderly thread of energy laid across a vast geometric loss. It holds because every part of the system accepts the weakness of the signal as the central condition of the mission. The radio beam is narrow, the power is limited, the energy fades, and still the message continues on its way, crossing darkness. as a nearly vanishing form that remains just strong enough to be heard. On Earth, the faint transmission from Voyager 1 can be heard only because a dedicated listening system has been built on a planetary scale. That system is the Deep Space Network, a set of large radio antenna complexes placed around the world so that communication with distant spacecraft can continue as Earth turns. A single antenna site cannot keep constant contact with a probe in deep space because the rotation of Earth carries that site out of view of the spacecraft for part of each day. Continuous listening therefore requires global geometry. The Deep Space Network solves this by distributing its stations across widely separated longitudes, traditionally in California, Spain, and Australia. As Earth rotates one site after another, gains the right position in the sky to point toward Voyager 1. In this way, the network turns a spinning planet into a continuous receiver. The arrangement is elegant in principle and demanding in practice. Each complex contains large dish antennas of extraordinary precision, supported by tracking systems, timing systems, signal processing equipment, and teams of specialists who coordinate use of the network among many missions. Voyager 1 is one of the most difficult targets they support because its signal is among the faintest, and because the spacecraft lies so far from Earth that every small weakness in the chain matters. The giant dishes of the network are essential because receiving a very weak signal depends strongly on collecting area. A larger antenna intercepts more of the incoming radio energy. Since the beam from Voyager 1 has spread across an immense region, by the time it reaches Earth, only a minute fraction of its power falls on any given area. The receiving dish must therefore be as large and efficient as possible. The curved surface reflects the incoming wave toward a feed system that passes the signal onward for amplification and analysis. Precision matters everywhere. The dish must hold its shape closely enough that the reflected waves remain properly focused. The pointing system must direct the antenna at the correct place in the sky with high accuracy. The timing systems must remain stable enough to support the long integrations and frequency tracking needed to recover the signal. These antennas are not simple metal balls turned loosely toward a bright source. They are scientific instruments built to detect structure in a whisper. Because Voyager 1 is so distant, tracking its exact position is itself part of the task. Earth does not merely know in a broad sense where to point. It uses refined orbit determination, signal timing, and repeated measurements to keep the expected location of the spacecraft accurate enough for narrow beam communication. The antenna does not hunt randomly through the sky. It follows carefully predicted geometry, corrected and improved over time. Even then, the process is not passive. The receiving systems must account for Earth's rotation, Earth's orbital motion around the Sun, the spacecraft's path outward, and other smaller influences on line of sight and frequency. This makes deep space reception an act of coordinated calculation as much as an act of listening. The network's global nature also creates operational continuity. When Voyager 1 sets below the horizon at one site, another site can take over when the geometry becomes favorable there. This handoff preserves contact over long intervals and allows mission teams to schedule communication windows according to scientific need, engineering need, and competition from other spacecraft also using the same antennas. The Deep Space Network is therefore both a scientific infrastructure and a scheduling system. Its time is valuable, and each session must be planned. For Voyager 1, such planning includes not only when the spacecraft is visible, but when its telemetry is most needed, when commands must be uplinked, and when long tracking passes can support careful study of its weak signal. Sometimes, the signal must be strengthened in practice by combining capabilities, using improved processing, or dedicating long observation periods to pull out the data. The network's role is not merely to hear strong transmissions when convenient. It is to make possible the hearing of transmissions that would otherwise disappear into silence. This listening is affected by Earth as well. Although space between Voyager 1 and Earth is largely transparent to radio communication, the final part of the path passes through Earth's atmosphere and into an environment crowded with human technology. The receiving sites are placed and protected to reduce radio interference, but the challenge remains serious. Weak deep space signals must be distinguished from natural noise, local electronics, terrestrial broadcasts, and the thermal background inherent in any physical receiving system. This makes site design shielding equipment, quality and operational discipline extremely important. The network is not just large, it must also be quiet in the radio sense. Only then can the giant dish serve its true purpose. One of the striking features of the deep space network is that it extends the effective size of human perception. A person standing near one of its antennas sees metal structure motors, cables, and support towers. But in operation, the dish becomes part of a far larger relationship. It couples Earth to a distant machine launched decades ago, and it does so through exquisite sensitivity rather than force. The antenna's great size is not a monument to power alone. It is a tool of attention. It allows the planet to lean in a technical sense toward a fading source in interstellar space. This is why the network occupies such an important place in the story of Voyager 1. The spacecraft may generate the signal, but Earth must deserve to receive it. That means building instruments large enough, accurate enough, and well-placed enough to catch what little arrives. It means maintaining a global chain of listening across decades. It means treating reception as a craft of precision under severe physical limits. Through this network, Earth remains an active participant in the mission, rather than a distant spectator. Voyager 1 sends a narrow beam into darkness, and the deep space network turns that darkness into a measurable path, using the rotation of the planet, the scale of its antennas, and the discipline of its operations to keep the faint conversation alive. By the time Voyager 1's radio transmission reaches Earth, the signal is so weak that receiving it is only the beginning of the problem. Hearing a distant carrier is not the same as understanding it. The message must be separated from noise, stabilized, measured, decoded, and checked before it becomes useful telemetry. This work happens within receiving systems designed to operate at the edge of detectability, where the arriving wave is far below the strength of ordinary radio communication and where every avoidable source of disturbance matters. The process begins after the giant dish of the deep space network has gathered and focused the incoming radio energy. That energy is passed into electronics that amplify the signal, but amplification must be done with great care. Any amplifier boosts not only the desired signal, but also the unwanted fluctuations already present in the system. These fluctuations are called noise. Some come from the environment, some from the electronics themselves, and some from the basic thermal motion of matter. Thermal noise is especially important because it is unavoidable. Every physical component at a temperature above absolute zero produces random electrical agitation. In strong communication systems, this background may be only a modest concern. In communication with Voyager 1, it becomes one of the central facts of the link. For that reason, receiving equipment is designed to add as little extra noise as possible. Engineers use very low-noise amplifiers placed early in the receiving chain so that the faint signal can be strengthened before later stages of processing introduce more disturbance. In some systems, sensitive components are cooled to reduce thermal noise further because colder electronics generate less random motion. The aim is simple in principle and difficult in practice. The receiving chain must preserve the fragile structure of the incoming wave without burying it under the receiver's own imperfections. Once amplified, the signals still cannot be read as ordinary sound or plain text. Voyager 1 does not send sentences. It sends a modulated radio carrier containing encoded digital information. The receiving system must first detect the presence of the carrier and lock onto its frequency with precision. This is complicated by the Doppler effect. Because Earth rotates, Earth orbits the Sun, and Voyager 1 moves through space, the apparent frequency of the received signal changes. The shift is usually small in relative terms, but for a very weak transmission, small errors matter. Receivers therefore use prediction and tracking to follow the carrier as its apparent frequency drifts. They do not merely tune once and remain fixed. They stay matched to the evolving signal so that its structure can be recovered accurately. After frequency tracking, the next task is to extract the information carried by the modulation. In digital telemetry, information is represented through controlled changes in the radio signal, which correspond to binary states that can be interpreted as ones and zeros. These bits are then assembled into larger patterns representing engineering measurements, instrument readings, and spacecraft status information. But at the edge of detectability, the bits do not arrive with perfect clarity. Noise can blur transitions, weaken confidence, and create ambiguity. To cope with this deep space communication, uses coding methods that make the message more recoverable. Instead of sending only the bare minimum data, the system includes structure that helps Earth infer the intended information, even when parts of the signal are uncertain. This is often described as error detection and error correction. Error detection reveals when data has likely been damaged. Error correction goes further by allowing some mistakes to be identified and repaired mathematically. The principle is powerful because it turns order into resilience. The signal does not need to arrive perfectly. It needs to arrive with enough intact structure that the intended pattern can still be reconstructed. This comes at a cost. Stronger coding usually reduces the net rate at which new information can be delivered, because some of the transmission capacity is spent on protective structure rather than fresh data alone. For Voyager 1, that trade is acceptable. The mission does not depend on speed in the ordinary sense. It depends on reliable recovery of weak information across extreme distance. The data rate is therefore very low compared with modern communication systems, but low rate helps preserve integrity. It allows the receiving system to spend more time gathering evidence for each bit, integrating the signal over longer intervals and improving the chance that the correct pattern emerges from noise. Integration is an important idea here. A weak signal that is hard to detect in an instant can become clearer when observed coherently over time as repeated structure accumulates while random fluctuations average out. This is one reason precise timing and frequency stability matter so much. If the receiver knows how the signal should behave, it can combine observations in a disciplined way and increase confidence in what is real. After the bits are recovered, computers on Earth organize them into telemetry frames, structured packets of information that correspond to different spacecraft systems. Engineers then read values for temperatures, voltages, currents, switch states, computer activity, instrument outputs, and other indicators of spacecraft health and scientific operation. Even this final stage requires interpretation. A number has meaning only within context. A voltage may be normal or troubling depending on system state. A temperature may be acceptable or dangerous depending on whether heaters are active. Telemetry is therefore not just data, but a language of condition translated from faint radio structure into engineering understanding. The remarkable feature of this entire process is that meaning survives such weakness. The signal arrives deeply submerged in background noise, shifted by motion, thinned by distance, and limited by power. Yet it still contains an ordered pattern that Earth can recover. That recovery is not an act of guesswork in the casual sense. It is the result of antenna gain, low-noise electronics, stable clocks, frequency, prediction, coding theory, and careful processing working together. Voyager. One's transmission becomes useful not because the signal is strong, but because the receiving system is patient enough, quiet enough, and mathematically disciplined enough to uncover what the spacecraft has said. In that way, decoding the telemetry is the moment when faint energy becomes knowledge, and where a nearly vanishing whisper from interstellar space is turned back into a readable account of a machine still alive in the dark. Voyager 1 continues to function at great distance, not because it is guided moment by moment from Earth, but because it carries within itself a limited and durable kind of self-management. Its onboard computer systems are small by modern standards, modest in speed and narrow in memory. Yet they are built around a central requirement of deep space flight. A spacecraft must remain orderly when human intervention is delayed. This requirement becomes more severe as distance grows. With many hours of one-way light time between Earth and the spacecraft, no controller can immediately correct a mistake, halt a harmful sequence, or answer an unexpected condition in real time. The craft must therefore sustain basic awareness of its own state and must follow predefined rules that help it remain safe when something goes wrong. In Voyager 1, that capacity is not intelligence in the broad human sense. It is structured autonomy, a careful arrangement of programs, subsystems, and fault responses, designed to preserve mission function under strict limits. The spacecraft contains more than one major computer role because deep space operation requires different kinds of work. Some functions handle command interpretation and system sequencing. Some handle attitude and articulation control, meaning the maintenance of spacecraft orientation and the movement of components that must point correctly. Some manage data formatting and the preparation of information for transmission. These roles are not separated to create luxury or complexity for its own sake. They reflect the fact that the spacecraft must sense, decide within narrow rules, act on stored instructions, and remain communicative, all with hardware rooted in an earlier era of engineering. Memory is extremely limited compared with anything common in later computing. Programs must be concise. Data storage must be managed carefully. New instructions cannot simply be added without thought, because the spacecraft has finite space for commands and finite tolerance for error. This constraint shapes the entire operational style of the mission. Engineers on Earth do not treat Voyager 1 as a flexible general-purpose machine. They treat it as a specialized system whose behavior must be understood at a detailed level before any change is attempted. Every upload enters a narrow ecosystem of existing routines, timing relationships and hardware assumptions accumulated across decades. The spacecraft's onboard software therefore matters not only as code, but as a living structure of mission memory. It contains sequences that govern how the craft points its antenna toward Earth, how it stabilizes its orientation using thrusters, how it collects and formats telemetry, how it protects itself when certain conditions appear abnormal, and how it transitions between operational states. Many of these functions are routine when everything works well. Their importance becomes most visible when conditions are disturbed. A spacecraft this far from Earth cannot depend on immediate rescue, so it includes fault protection logic. Fault protection means that when certain indicators move outside expected ranges, or when specific failures are detected, the craft can shift itself into a safer mode. This may involve reducing activity, reorienting for communication, switching operational paths, or preserving core functions while waiting for further commands. Such behavior is conservative by design. In uncertainty, the spacecraft chooses survival over ambition. That choice reflects deep space reality. A temporarily interrupted science activity is acceptable. Loss of stable communication or attitude control may not be. Autonomy also governs the execution of command sequences sent from Earth. Because light time is long, engineers often send carefully structured sets of commands that Voyager 1 stores and carries out later according to schedule or condition. This creates a distributed form of action. Earth does not merely order a single step and wait for a reply. It often prepares a chain of activity that the spacecraft must perform correctly on its own. Timing sequence logic and system dependencies therefore matter greatly. A command that seems simple in isolation may affect power allocation, data handling, pointing requirements, or fault thresholds elsewhere in the spacecraft. The onboard computers must hold these relationships together. Their reliability over decades is one of the quiet achievements of the mission. Electronics in space face radiation, aging materials, temperature, stress, and cumulative wear. Memory elements can degrade. Bits can flip. Components can fail in ways that would be corrected easily on Earth by replacement, but cannot be repaired physically in deep space. The spacecraft must therefore endure not only the emptiness around it, but the gradual internal risk of long-term hardware aging. This makes simplicity valuable. Systems that are narrow, well-characterized, and designed with margin can sometimes last far beyond their expected lifetime. Voyager 1 demonstrates this principle clearly. Its computers are not powerful, but they are understandable. Their limits force caution, and caution can support longevity. Another important feature of onboard autonomy is attitude maintenance. Communication depends on keeping the high-gain antenna pointed toward Earth, while many scientific measurements depend on keeping instruments in their required orientations. To do this, the spacecraft uses reference information from sensors and applies controlled thruster firings to preserve alignment. These firings must be economical because fuel is limited and must remain usable over decades. The control system therefore balances accuracy, stability, and conservation. If orientation begins to drift too far, the result is not merely geometric inconvenience. Communication quality can fall. Solar illumination geometry can change, and instrument behavior may be affected. The spacecraft's internal ability to preserve pointing is therefore part of its ability to remain in contact at all. In practical terms, the onboard computers make Voyager 1 into a machine that can keep a disciplined routine while far from human hands. It can accept commands, store them, carry them out, monitor itself, react to certain failures, protect core systems, and maintain the alignment needed for continued survival. None of these abilities is unlimited. The system is not adaptive in an open-ended sense. It cannot invent new procedures or reason creatively about unfamiliar circumstances. That work remains on Earth, where engineers interpret telemetry and design responses. But between Earth's long-delayed decisions, the spacecraft must remain a competent steward of its own narrow world. This is what gives its autonomy such importance. Voyager 1 continues through interstellar space with a small and aging computational mind, carrying not speed or abundance, but order. In that order lies the ability to endure light-time delay, to survive between commands, and to remain a readable, controllable presence at a distance where immediate control is impossible. The spacecraft's brain is simple, old, and constrained, yet it has proved sufficient for one of the longest operational lives ever sustained by a human-made machine. The long life of Voyager 1 depends on a source of energy very different from the large solar arrays that power many spacecraft closer to the Sun. At the great distances reached by the outer planets and beyond, sunlight weakens so severely that solar power becomes impractical for a mission of this kind. The spacecraft instead relies on radioisotope thermoelectric generators, often called RTGs devices, that turn the natural heat of radioactive decay into electricity. This choice is central to the mission's endurance. Without it, Voyager 1 could not have crossed the giant planets and continued onward into interstellar space while still operating instruments, computers, heaters, thrusters, and its radio transmitter. The RTG system begins with a radioactive material plutonium-238, prepared in a form that steadily releases heat as its atomic nuclei decay. Radioactive decay is a natural process in which unstable nuclei transform and emit energy. In this case, the emitted energy is mostly carried away in particles that quickly deposit their motion as heat inside the generator structure. The process is not explosive, and it does not resemble the chain reaction used in nuclear reactors. It is slow, predictable, and continuous. That steadiness makes it useful for deep space missions. The heat appears day and night, near planets and between stars, independent of sunlight shadow orientation or season. As long as enough plutonium remains and the generator hardware continues to function, the spacecraft has a persistent source of thermal energy. Turning that heat into electricity requires thermoelectric conversion. This depends on the Seebeck effect, a physical principle in which a temperature difference across certain materials creates an electrical voltage. In simple terms, one side of a thermoelectric element is kept hot by the decaying plutonium, while the other side is kept cooler by radiating heat into space. The difference in temperature allows charge carriers in the material to move in a way that produces electrical power. The process has no spinning turbine, no pump, and no large moving mechanical assembly. That simplicity matters. In deep space, a system with few moving parts often offers great reliability over long spans of time. The generator is therefore not highly efficient by the standards of terrestrial power plants. But efficiency is not the only measure that matters. For Voyager 1, reliability, predictability, and independence from sunlight are more important than extracting the highest possible fraction of energy. At launch, the RTGs produce substantially more electrical power than the spacecraft requires in its final reduced state many decades later. This margin is not excess for comfort. It is a necessary allowance for decline. The plutonium does not stop decaying, but the rate at which it releases heat gradually falls as the amount of undecayed material decreases. In addition, the thermoelectric elements themselves degrade over time. Their ability to turn heat into electricity becomes less effective as the years pass. The result is a slow and unavoidable decrease in available electrical power. This decline is built into the mission from the beginning. Engineers know that every year the spacecraft will have a smaller electrical budget, and that the full set of systems active in the early mission cannot remain active forever. The RTGs also shape Voyager 1 thermally as well as electrically. They are sources of heat in a cold environment, and that heat influences spacecraft temperatures, especially early in the mission. But most of the thermal energy produced by the generators does not become electricity. It is rejected as waste heat and radiated away into space. Managing this thermal environment is part of the spacecraft's overall design. Too much retained heat in one area and too little in another can both create difficulties. In the outer solar system and beyond, where the surrounding environment offers almost no warmth, internal heat sources become precious. As power declines and heaters are turned off to conserve electricity, the thermal contribution of the RTGs becomes even more significant in helping parts of the spacecraft remain above critically cold conditions. The choice of plutonium-238 is especially important because it offers a useful combination of high heat output per unit mass and a decay rate suitable for multi-decade missions. A power source for deep space must not fade too quickly, yet it must also provide enough heat to justify the mass carried at launch. The isotope used in Voyager strikes a balance that makes such missions possible. Its gradual decline is the price paid for long duration. There is no refueling. There is no restart. There is only a slow narrowing of capability over time. In this sense, the RTGs give Voyager 1 both life and a measurable path toward eventual silence. Every subsystem on the spacecraft depends on the electricity they provide. The computers need it to interpret commands and manage operations. The transmitter needs it to send telemetry back to Earth. The scientific instruments need it to sense particles fields and plasma in the interstellar medium. The thruster control systems need it to maintain orientation. Even temperature survival often depends indirectly on power, because heaters and thermal management systems compete for the same shrinking electrical pool. When engineers decide which functions to preserve and which to deactivate, they are responding to the gradual decline of RTG output. The power source, therefore, does not sit in the background of the mission as a passive utility. It is the central metabolic system of the spacecraft, the quiet provider that determines what remains possible at every stage of late mission life. What makes the RTG story remarkable is not only that it works, but that it continues to work after so many decades. A device built in the technology culture of the 1970s still converts nuclear decay into useful electricity while traveling through interstellar space. Its output is much lower than it once was, and every remaining watt must be treated carefully. But the principle remains sound. Heat continues to flow from atomic transformation. A temperature difference continues to form. Electrical current continues to emerge. Through that chain, Voyager 1 remains active. Its power is not abundant, and it is not renewable in the ordinary sense, yet it is stable enough to have supported one of the longest scientific journeys ever achieved. The radioisotope generators make this possible by offering exactly what deep space demands most, not brilliance, but endurance. They provide a steady inner fire, slowly weakening, never hurried, carrying the spacecraft onward through darkness, while still leaving enough strength for one more transmission home. As the electrical output of Voyager 1's radioisotope generators declines year by year, the mission enters a long phase of deliberate reduction. This is not a sudden collapse, but a managed narrowing of life. Every lost watt matters because the spacecraft still depends on electricity for communication, computation, attitude control, and scientific measurement. The available power does not fall in large dramatic steps at first. It decreases gradually, quietly, and without negotiation, following the steady decay of plutonium and the aging of the thermoelectric system. Against that steady loss, NASA responds with a series of choices intended to preserve the most essential functions for as long as possible. These choices are not only technical, they are also strategic. They ask what the spacecraft must continue doing in order to remain scientifically valuable and operationally alive, and what functions can be surrendered in exchange for more time. The answer changes as the mission changes. During the planetary encounters, Voyager 1 carries a broader set of active tasks. It must operate cameras, instruments, data systems, and pointing sequences suited to close observation. In interstellar space, the priorities are different. Imaging is no longer central. The surrounding environment is sparse, and the targets are not worlds with visible surfaces, clouds and rings, but particles, magnetic fields, plasma, and the large-scale structure of the medium beyond the heliosphere. As a result, some instruments that were once vital become unnecessary, while others remain scientifically important. This shift gives mission planners a way to adapt to declining power. Instruments no longer needed can be turned off. Subsystems that support former goals can be deactivated. What remains is a leaner spacecraft focused on the outermost scientific questions and on the preservation of communication itself. Power management on Voyager 1 is therefore an ongoing act of triage. The word suggests urgency, but in this case the process is patient-measured and informed by long familiarity with the spacecraft. Engineers track the electrical budget closely. They know how much output remains, how much each subsystem consumes, and what the projected decline will do over future years. They then plan a sequence of reductions intended to stay slightly ahead of crisis. Rather than wait for a dangerous shortfall, they remove non-essential loads in advance. This creates margin, however small, and reduces the risk of uncontrolled shutdowns. The decisions can be difficult because every deactivated system closes off a capability. An instrument switched off may never be used again. A heater disabled may expose hardware to greater thermal stress. A convenience preserved for too long may threaten a more central function later. The mission therefore becomes increasingly defined by prioritization. Communication almost always stands near the top of that hierarchy, because without the radio link, the spacecraft cannot return data and cannot receive commands. The onboard computers and command systems are also indispensable because they sustain control and interpretation. Attitude maintenance remains crucial because the high-gain antenna must stay pointed toward Earth. Scientific instruments survive only insofar as they can coexist with those foundations. Even among the instruments, some are more valuable than others in the interstellar phase. Systems that measure the local plasma environment, energetic particles and magnetic fields can continue to produce meaningful science long after the camera era has ended. The power budget therefore becomes a map of purpose. It reveals what the mission now is by showing what the mission still supports. There is also a subtle relationship between power and risk. Turning off a subsystem can save electricity, but it may also change the spacecraft's thermal balance or reduce redundancy. A heater, for example, consumes power that might otherwise support an instrument, but the heater also helps keep lines, valves, electronics, or sensors within safer temperature ranges. Disabling it extends electrical margin while increasing exposure to cold. The spacecraft must therefore rely on its inherent resilience, the conservatism of its design, and the possibility that hardware may continue working below rated temperatures. In some cases, that resilience has been stronger than expected, allowing systems to function in colder conditions than engineers originally considered ideal. This does not eliminate risk. It simply means the mission can sometimes choose endurance over comfort and succeed. Another part of the survival strategy involves timing. Power does not vanish all at once, so the mission can schedule reductions in a sequence that extracts maximum science from the remaining years. A subsystem may be preserved until the data it provides is judged less valuable than the extra time that could be bought by turning it off. This creates a moving frontier between present usefulness and future survival. The decision is rarely about whether a function is valuable in absolute terms. It is about whether that value is worth its cost in dwindling watts. In that sense, late Voyager operations resemble life support in a remote habitat. The system remains alive by reducing itself, carefully preserving the core, and accepting that not every useful function can continue indefinitely. These choices also depend on deep knowledge of the spacecraft's behavior. Voyager 1 is not a generic machine. It is an old and singular one, with decades of operational history, unexpected endurance, past anomalies, and a thermal and electrical character understood through long experience. Engineers know where the margins are narrow, where the craft has surprised them by surviving, and where small adjustments can produce meaningful savings. They are not managing power through abstract theory alone. They are working with an intimate technical memory of a specific spacecraft aging in the dark. This makes the survival strategy partly scientific and partly historical. Every decision draws on what the craft has been, as well as what it still must be. The result is a mission that continues not through abundance, but through disciplined subtraction. Voyager 1 keeps moving outward, but its internal life becomes simpler over time. Systems fall silent one by one. The electrical budget tightens. The definition of necessity sharpens. Yet the narrowing is not empty loss. It is what allows the essential functions to persist. NASA keeps the spacecraft alive by accepting decline, by refusing waste, and by shaping the remaining power into a form that can still support contact and science. In this way, the mission survives, not by escaping the fading of its energy source, but by matching its operations to that fading with care. The craft continues, because every remaining watt is treated as time made visible. Beyond the orbit of the outer planets, and later beyond the boundary where the Sun's outward influence weakens into the wider galactic medium, Voyager 1 enters a thermal world far colder than the one imagined in ordinary human experience. Space is often described as empty and cold, but for a spacecraft, the meaning of cold is specific. Temperature is shaped not by surrounding air, since there is almost none, but by the balance between absorbed energy, generated heat, stored heat, and radiated heat. Near Earth, sunlight is still strong, and thermal design can rely on a more generous external energy environment. For Voyager 1 in deep space, sunlight has faded to a thin contribution. What remains most important is the heat produced inside the spacecraft itself and the rate at which that heat escapes into space. As electrical power declines and systems are turned off to preserve mission life, the amount of internal heat available to warm the spacecraft also declines. This creates one of the most delicate late mission conditions. The same act that saves electricity can make the spacecraft colder. The struggle for survival therefore becomes both electrical and thermal at once. In the early years of the mission, heaters and active subsystems help maintain internal temperatures with more margin. The radioisotope generators also contribute substantial waste heat that influences the spacecraft's thermal state. Over time, however, as generator output falls and mission planners shut down non-essential loads, the thermal budget narrows. Heaters become tempting targets for conservation because they consume power without directly producing scientific data or communication. Yet they serve a protective role. They keep instruments, fuel lines, thrusters, valves, electronics, and sensors within temperature ranges considered safe or at least preferable. When a heater is switched off, the spacecraft gains electrical margin but loses thermal comfort. That trade becomes more severe as the mission ages. The structure cools. Individual components drift below their originally intended operating temperatures. Materials contract. Lubricants, seals, and mechanical tolerances face conditions that may not have been expected to persist for such a long period. The remarkable fact is that many systems have continued to function anyway. This endurance does not mean temperature limits are imaginary. It means the spacecraft has proved more resilient than the conservative expectations of design documentation alone. Some parts continue operating below their nominal temperature range because the underlying hardware retains enough margin, because actual deep space conditions are stable in certain ways, and because the mission teams have learned through careful observation how much cold the craft can tolerate. That lesson is never casual. Engineers do not assume survival merely because a system endured once before. They monitor telemetry, compare trends, and judge where cold is becoming dangerous. A temperature reading on Voyager 1 is not just an engineering number. It is evidence of whether the spacecraft's inner environment remains compatible with continued function. The cold affects different systems in different ways. Electronic components may experience altered behavior when temperatures fall far enough, though many space-qualified parts are designed with broad tolerance. Structural materials can shrink, slightly changing alignments or stresses. Sensors may drift. More subtle and worrying effects can appear in propulsion hardware. Voyager 1 depends on small thrusters to maintain orientation, and orientation is necessary for keeping the high-gain antenna pointed toward Earth. If thrusters or their propellant lines become too cold, response may weaken or reliability may drop. This makes the thermal condition of the propulsion system especially important. Communication, pointing, and survival all rest indirectly on the spacecraft remaining warm enough in the right places. The challenge is intensified by the fact that space offers no simple refuge. There is no surrounding warm medium to slow the cooling. Heat lost by radiation simply leaves. Thermal control therefore depends on insulation, internal heat distribution, spacecraft geometry, and selective use of heaters. The spacecraft is built with multi-layer insulation, a blanket-like system that reduces radiative heat loss, but insulation can only retain heat that exists. As power declines, the available heat becomes scarcer. In late mission life, the craft survives partly by accepting temperatures that earlier mission planners might have considered too low for comfort. This is not recklessness. It is adaptation to unavoidable decline. The alternative would often be to preserve warmth at the cost of shutting down more central functions sooner. Mission teams therefore make careful decisions about where cold can be tolerated and where it cannot. Some heaters are turned off because the hardware they protect seems likely to endure. Others remain longer because their loss would place crucial systems at too much risk. The spacecraft becomes, in effect, a body redistributing warmth under conditions of scarcity. Its surviving life depends on which internal regions can afford to cool and which must remain guarded. There is also an important asymmetry in these decisions. Saving electricity by shutting off a heater produces an immediate and measurable gain in power margin. The thermal harm may emerge slowly, ambiguously, or only after prolonged exposure. This means each decision carries uncertainty. A component might continue functioning for years in colder conditions than expected, or a long period of low temperature might gradually create a failure that has no simple reversal. Engineers must therefore weigh present survival against future vulnerability. They do so by using telemetry trends, design history, environmental models, and the accumulated record of how Voyager 1 has behaved over decades. The spacecraft itself becomes the final judge because only its continued functioning reveals where the real boundaries lie. What emerges from this long encounter with cold is a portrait of endurance under diminishing warmth. Voyager 1 is not preserved by comfort, but by a disciplined tolerance for hardship. Systems once protected more generously now persist with less. Instruments remain active in a spacecraft that has grown colder year by year. Thrusters, computers, and communication hardware continue operating in an environment more severe than their ordinary working life ever promised. The mission's later years are therefore shaped by an unusual fact. The craft stays alive, not because cold has been eliminated, but because enough of its hardware can still function within it. Every continued transmission from Voyager 1 carries that thermal story inside it. Behind the numbers in the telemetry lies a machine that has survived by surrendering warmth selectively, by conserving power at the edge of risk, and by proving again and again that design margins combined with careful management can sustain life in conditions far harsher and longer than originally required. In the deep cold beyond the familiar solar system, Voyager 1 continues not in ideal temperature, but in stubborn balance held together by fading heat insulation and the refusal of crucial systems to stop working. One of the most remarkable late chapters in Voyager 1's life begins not with a dramatic mechanical failure, but with something quieter and more difficult. The spacecraft continues to send a steady radio signal, yet the information inside that signal no longer makes sense. From Earth mission controllers can still tell that Voyager 1 is alive. It continues to hear commands. It appears to hold its orientation and basic operation. But the science and engineering data returning from the spacecraft become unreadable. The voice is present, but its language has broken. This kind of problem is especially unsettling in deep space because it sits between life and silence. A dead spacecraft is tragic but clear. A spacecraft that still responds yet no longer speaks intelligibly creates a narrower and more technical mystery. Somewhere inside the chain that gathers packages and transmits telemetry order has been lost. Engineers on Earth must solve that mystery without direct access, without immediate feedback, and across a one-way light time of more than 22 hours. The issue is traced to one of Voyager 1's onboard computers, the Flight Data Subsystem. This system is responsible for packaging science and engineering information before it is handed onward for transmission to Earth. In simple terms, it helps turn the spacecraft's internal state and instrument readings into a structured message. If that structure fails, the radio signal may remain healthy while the contents become useless. That is exactly the kind of failure the team faces. The carrier arrives, but the data stream is corrupted. Because the spacecraft is so far away, even the act of investigating takes on an unusual shape. Engineers cannot probe the machine directly. They must send carefully chosen commands, wait nearly a day for those commands to arrive, then wait nearly another day for the response to come back. Each attempt to learn more consumes time on a scale that would feel intolerable in most other technical settings. Here, it becomes normal. The process begins with inference. Teams compare what still works with what no longer works. They reason from preserved functions to damaged ones. Since Voyager 1 still appears to receive commands and maintain basic operation, the problem is likely not total system collapse. It is more local, though local on a spacecraft of this age can still mean deep and difficult. The team eventually identifies evidence pointing to a damaged memory area in the flight data subsystem. A single failed memory chip appears to have affected a portion of stored software code. That detail matters because onboard memory does not only hold temporary data. It also holds instructions, the logic required for the computer to perform its tasks. If part of that code is lost or corrupted, the system may continue running in a crippled state, transmitting patterns that no longer correspond properly to meaningful telemetry. The breakthrough comes through a mixture of patience, old knowledge, and inventive engineering. The team sends a special command, sometimes described informally as a gentle prompt intended to encourage the spacecraft to reveal more about the condition of the affected computer. What comes back is not immediately readable in the ordinary mission format, but it contains something precious, a memory readout. An engineer working with the Deep Space Network helps decode this unusual return, allowing the mission team to inspect the contents of the flight data subsystem's memory. That is an extraordinary moment. Across more than 15 billion miles, a spacecraft built in the 1970s has effectively exposed part of its own damaged internal state for diagnosis by people on Earth. This readout allows engineers to compare the altered memory with earlier expected patterns and identify where software has been lost. Once the failed chip is understood, a new problem appears. The damaged hardware itself cannot be repaired. No one can replace the chip receipt aboard or physically restore the missing memory. The only available path is to work around the damage using what still remains. That means relocating the affected code to other parts of the flight data subsystem's memory. But even this is not simple. The available free memory is fragmented. No single remaining location is large enough to hold the entire displaced section. The team must therefore divide the code into separate pieces and place those pieces in multiple locations. Then they must modify the software so those pieces still function together as a coherent whole. References to memory locations elsewhere in the program must also be updated so that instructions, variables, and data paths still point to the right places. This is surgery performed by radio, with long delays between every step on a machine older than many of the people helping to save it. The repair unfolds gradually. First, the code responsible for packaging engineering data is moved and adjusted. The command is transmitted outward. The long wait begins. When the response returns, mission controllers see something they have not seen in months: usable engineering telemetry. Temperatures, voltages, and system states become readable again. The spacecraft's internal condition, which had been hidden behind nonsense, comes back into view. That partial recovery is both practical and symbolic. Practically, it gives engineers the information needed to continue the repair. Symbolically, it means Voyager 1 has found its way back to intelligibility. In the following weeks, additional sections of code related to science data are relocated and corrected. Step by step, more of the spacecraft's voice is restored. Eventually, the science instruments return usable data again, and normal science operations resume. What makes this episode so striking is not merely that a problem was solved, but how it was solved. The repair depends on deep historical knowledge of the spacecraft's architecture, on the ability to read obsolete software structures, on the willingness to reason carefully through damaged memory maps, and on the discipline to act through delays that turn every experiment into a multi-day event. It also depends on a kind of continuity rare in technology. Voyager 1's designers could not have foreseen every anomaly that would arise after nearly half a century in flight, yet their system retained enough flexibility for later generations to invent a path around failure. The mission team, in turn, retained enough understanding of that old design to use flexibility that had never been intended for this exact purpose. In this sense, the remote repair is not magic, though it can seem miraculous from a distance. It is the product of old hardware durable design, precise communication, and human persistence joined across time. Voyager 1 continues outward through interstellar space with damaged memory, rearranged code, and a restored capacity to speak. The spacecraft survives, not because it remains untouched by failure, but because even failure can sometimes be folded into a new working order, when knowledge, patience, and imagination travel farther than any hand ever could. Long before Voyager 1 becomes a remote station in interstellar space, it enters the realm of Jupiter. And there, the mission first reveals how much a passing spacecraft can change scientific understanding. Jupiter is the largest planet in the solar system, a world so massive that it shapes the motion of neighboring bodies and bends the paths of spacecraft that pass near it. For Voyager 1, Jupiter is both destination and turning point. The encounter is not only a chance to observe a giant planet closely, but also a chance to use the planet's gravity to redirect the spacecraft outward towards Saturn. This use of gravity is often called a gravity assist. In simple terms, the spacecraft falls into the moving gravitational field of a planet and leaves with a different path and speed relative to the Sun. The planet loses an imperceptibly small amount of orbital energy, while the spacecraft gains a significant advantage. This technique allows a mission launched with limited energy from Earth to reach distant worlds that would otherwise require far larger rockets. Yet the gravity assist is only one layer of the Jupiter encounter. The greater scientific transformation comes from what Voyager 1 sees. As the spacecraft approaches, Jupiter changes from a bright point into a structured world of bands, storms, moons, rings, and radiation. Its atmosphere appears first as a broad system of alternating light and dark belts circling the globe. These bands reflect large-scale winds moving in opposite directions at different latitudes. The visible clouds are composed mainly of compounds involving hydrogen, helium, ammonia, and other trace substances arranged by temperature, pressure, chemistry, and circulation. The atmosphere is not a flat skin over a solid surface. Jupiter has no ordinary solid surface like Earth. The visible cloud tops are part of a deep gaseous envelope that extends downward into increasingly compressed layers. In those depths, pressure rises enormously, and matter takes on forms unlike anything in everyday human experience. Voyager 1 does not penetrate that depth directly, but its close images and measurements reveal the outer atmosphere as a dynamic system of turbulence, wave patterns, vortices, and long-lived storms. The most famous of these is the Great Red Spot, a vast, rotating storm larger than Earth. Seen by Voyager 1, it is not a simple colored patch, but a structured atmospheric feature with internal motion and surrounding interactions that show the complexity of Jupiter's weather. Lightning cloud texture and the layered character of the atmosphere all suggest a world in constant motion, driven by both solar energy and a large supply of internal heat escaping from the planet's interior. Jupiter radiates more energy than it receives from the Sun, and that extra heat helps power convection and circulation on a grand scale. Around the planet, Voyager 1 also helps reveal a more complete understanding of Jupiter's magnetosphere, the enormous region dominated by its magnetic field. Jupiter's magnetic field is exceptionally strong, trapping charged particles and creating an intense radiation environment. This magnetosphere is not a quiet shell. It is a complex system shaped by the planet's rapid rotation, its internal magnetic dynamo, the solar wind, and the material supplied by its moons. For a spacecraft, this radiation environment presents a technical challenge as well as a scientific opportunity. Instruments can measure particle populations and field behavior, but electronics must survive their effects. Voyager 1's data show how immense and energetic this Jovian environment is, extending far into space and influencing the region around the planet in ways more like a small planetary system than a single isolated world. The spacecraft also discovers that Jupiter has a faint ring system, much less obvious than Saturn's, but scientifically important because it shows that rings are not unique to one giant planet. These rings are thin and dark, made of fine particles that are difficult to see except under favorable viewing geometry. Their existence broadens understanding of how dust and small debris can persist around planets supported and replenished by ongoing processes. Yet, perhaps, the most profound discoveries of the Jupiter encounter come from the moons. Before Voyager, the Galilean moons are already known as major worlds in their own right, but close observation transforms them from points of light into distinct planetary bodies with separate histories and geologies. On Ganymede and Callisto, ancient cratered surfaces show long exposure to impacts and reveal different patterns of terrain evolution. Europa appears smoother and brighter, crossed by lines and fractures that suggest a surface of water ice reshaped by stresses and internal activity. Even before later missions explore this idea more fully, Voyager 1 helps establish Europa as a world of special interest, one whose frozen exterior hints at deeper complexity. The most astonishing revelation comes from Io. Before Voyager, Io is expected to be a heavily cratered moon, like many other solid bodies in the outer solar system. Instead, Voyager 1 observes evidence of active volcanism, the first volcanic activity ever seen beyond Earth. Plumes rise above the surface. Fresh deposits spread across the landscape. The expected record of old impacts is disrupted by ongoing resurfacing. This discovery changes planetary science immediately. It shows that a moon can remain intensely active far from the Sun if another energy source is available. In Io's case, that source is tidal heating. Jupiter's gravity, together with the gravitational influence of neighboring moons, repeatedly flexes Io's interior. This constant flexing generates heat, which then drives volcanic activity. The result is a world transformed by orbital mechanics into one of the most geologically active places in the solar system. This insight has wide consequences because it demonstrates that heat and activity do not depend only on size or sunlight. Orbital relationships can create internal energy and sustain dynamic worlds in unexpected settings. The Jupiter encounter therefore becomes a first great flowering of Voyager science. A spacecraft sent outward on a carefully timed path uses Jupiter's gravity to continue deeper into the solar system. But in doing so, it also reveals that giant planets are not merely large spheres, and that moons are not merely minor companions. Jupiter emerges as a system of atmosphere magnetism, radiation dust, and active worlds. Its environment is layered, energetic, and full of interactions. For Voyager 1, this is the first great outward opening of the mission. The spacecraft arrives to gain speed, but it leaves having transformed human knowledge of a giant planet and its family of moons. The encounter shows that the outer solar system is not empty distance between destinations. It is a region of rich physical processes where weather gravity, magnetic forces, and hidden internal heat combine to create worlds far stranger and more varied than earlier telescopes alone had been able to reveal. Crossing from the heliosphere into interstellar space is often imagined as a clean moment, a simple passage from one side of a border to the other. Voyager 1 shows that the reality is more subtle. There is a crossing, and it can be dated with scientific confidence, but the evidence does not arrive all at once in a single obvious sign. Instead, the transition is recognized through a combination of changes in particle populations, plasma conditions, and magnetic behavior that together reveal that the spacecraft has moved beyond the Sun's outer bubble into the very local interstellar medium. The phrase very local interstellar medium refers to the thin material in the galaxy immediately surrounding the heliosphere, the nearby portion of interstellar space through which the solar system moves. When Voyager 1 reaches this region in 2012, it becomes the first human-made object to enter it directly. Yet even that statement carries an important caution. The boundary, called the heliopause, is real, but it is not like a painted line in empty space. It is the place where the outward pressure of the solar wind is balanced by the pressure of the interstellar medium. Because both environments are made of plasmas and magnetic fields, the transition between them is governed by charged particles' field geometry and motion, rather than by any solid surface. The first strong clues that Voyager 1 is nearing this frontier come from energetic particles. Instruments on the spacecraft record a sharp decline in lower energy charged particles associated with the heliosphere and a rise in higher energy galactic cosmic rays arriving from outside. This shift is striking because it suggests that the Sun's shielding influence has weakened dramatically at the spacecraft's location. The local particle environment no longer looks like the outer heliosheath alone. It begins to resemble the galaxy beyond. At first, however, the interpretation is not simple. Scientists expect that if Voyager 1 has crossed into interstellar space, the magnetic field direction should show a marked change. Early observations do not display the dramatic turning many had anticipated. Instead, the magnetic field beyond the apparent crossing seems unexpectedly similar in direction to the field just inside. This creates one of the most interesting scientific puzzles in the mission. The particle evidence points toward a boundary crossing, but the magnetic geometry does not behave in the neat textbook way some models had encouraged people to imagine. The result is a period of cautioned debate and careful interpretation. The mission team does not rush to declare success on the basis of one clue alone. What helps resolve the question is plasma density. Voyager 1's plasma instrument is no longer operating in the ordinary direct measurement sense, but other instruments can still detect plasma oscillations caused when disturbances pass through the surrounding medium. These oscillations act like a diagnostic of electron density. When a solar eruption eventually sends a pressure wave outward, and that disturbance reaches Voyager 1, it excites plasma oscillations in the local medium. By measuring the frequency of those oscillations, scientists can infer the surrounding plasma density. The result is decisive. The density around Voyager 1 is much higher than expected for the outer heliosphere and matches what is expected for interstellar plasma. That finding gives strong support to the conclusion that the spacecraft has crossed the heliopause and entered interstellar space. The crossing is therefore identified not by a single dramatic sign, but by a convergence of evidence: the drop in heliospheric particles, the increase in galactic cosmic rays, and the later confirmation that the surrounding plasma density is characteristic of the interstellar medium. The magnetic field puzzle remains important, though. Instead of overturning the crossing, it teaches something more subtle about the shape and behavior of the boundary. It suggests that the magnetic field outside the heliopause can be draped or aligned in ways that make the transition less visually abrupt in field direction than some simpler expectations predicted. In other words, the real heliopause is more intricate than a schematic drawing. The Sun's field and the interstellar field meet under conditions shaped by local geometry, plasma flow, and three-dimensional structure. Voyager 1 samples only one path through that complexity. Later measurements by Voyager 2 reinforce the idea that the field alignment seen by Voyager 1 is not merely a meaningless accident, though each crossing occurs at a different place and under different solar conditions. The boundary is thus both real and nuanced. That combination is one of the central lessons of the crossing. In the very local interstellar medium, Voyager 1 continues to detect a region that is not empty in any everyday sense. It contains plasma magnetic field and galactic cosmic rays. The density is still extraordinarily low by earthly standards, but it is higher than the solar wind plasma just beyond the heliopause had led some to expect. The local interstellar plasma also appears somewhat compressed near the boundary, showing that the heliopause is part of an interaction zone rather than a passive limit. Pressure fronts and shocks can still travel through this medium, and Voyager 1 has observed some of these disturbances in the years after crossing. The Sun has not ceased to matter entirely just because the spacecraft is outside the heliosphere. Solar activity can still send large-scale disturbances outward that propagate through the surrounding interstellar plasma and reach the spacecraft later. This gives the region a mixed character. It is interstellar space, but it is interstellar space in the immediate neighborhood of the Sun's boundary, not a disconnected galactic wilderness. The crossing also changes the meaning of Voyager 1's science. Earlier phases of the mission focus on planets' moons and boundary layers within the Sun's domain. After the heliopause, the spacecraft becomes a direct monitor of the local galactic environment itself. Its measurements are sparse in type compared with the rich variety of planetary imaging, yet they are profound in significance. They tell humanity what the nearest interstellar space is like, not through remote inference, but through contact. The medium has a measurable plasma density, a measurable magnetic field, a measurable particle population. The galaxy becomes not only a distant backdrop, but a sampled environment. This is why the heliopause crossing carries such scientific and symbolic weight. It marks the point at which a machine launched from Earth ceases merely to travel far within the solar system and begins to report from beyond the Sun's protective bubble. Still, the meaning of that moment is best preserved by resisting oversimplification. Voyager 1 does not burst through a wall into a wholly separate universe. It moves through a complex plasma boundary whose signs must be interpreted carefully. The evidence arrives in stages. Expectations are partly confirmed and partly revised. The resulting picture is richer than the older, simpler one. The heliopause is crossed in 2012, but the understanding of what that crossing means grows through data analysis and comparison. Voyager 1 enters interstellar space, and in doing so, it shows that even the gateway between the Sun and the galaxy is layered with surprise. where a boundary long imagined in theory becomes at last a place of measured reality. Voyager 1 now moves through interstellar space on a path that will continue long after its mission systems fall silent. Its remaining active life is measured not by distance, because distance will go on increasing for ages beyond human institutions, but by power. The spacecraft still functions because a shrinking electrical supply continues to support a narrow set of essential systems: communication, basic computing, attitude control, and a diminishing collection of scientific instruments. Each year, the margin becomes smaller. Each year, mission engineers reconsider what can still be preserved and what must be allowed to end. This final phase of operation is therefore not a race toward a last destination. It is a managed approach toward silence. The spacecraft does not fail in a single dramatic instant. It moves toward a future in which one instrument after another is turned off or becomes impossible to sustain, until eventually there is not enough power left to maintain the conditions required for communication with Earth. That future has long been expected. It is not a surprise hidden within the mission. It is built into the nature of the spacecraft's power source and into the age of its hardware. What gives it emotional force is the contrast between the slow certainty of that ending and the extraordinary persistence that has already preceded it. Voyager 1 has survived far beyond its original primary mission. It has crossed the giant planet region, traversed the heliosphere, passed beyond the heliopause, and continued to send meaningful data from the local interstellar medium. The remaining years are therefore less about proving longevity than about using the last available watts with care. In practice, this means that mission life is extended through a sequence of sacrifices. Instruments are evaluated for scientific return against electrical cost. Heaters are reduced where survival seems possible without them. Operational modes are simplified. The spacecraft is stripped toward its essentials, not because those other functions were unimportant, but because survival now depends on preserving the core. This narrowing gives the mission a distinctive late character. In its youth, Voyager 1 is a broad explorer, equipped to image worlds, measure fields, study particles, and carry out a complex sequence of planetary observations. In old age, it becomes a minimal but still profound witness, reporting from a remote environment with only the systems that declining power can still sustain. At some point, perhaps through planned shutdowns, perhaps through the inability to keep a critical system alive, the flow of usable science data will end. Later, still communication itself will become impossible. That final loss may come because the transmitter can no longer be supported, because attitude control cannot be maintained reliably enough to keep the antenna pointed at Earth, or because another foundational system falls outside the range of what dwindling power can sustain. After that, Voyager 1 will not be dead in a biological sense, because it was never alive, but it will become inactive in the operational sense that matters to the mission. It will no longer send telemetry. It will no longer receive commands in any meaningful way. It will continue along its path as a silent object carrying its structure, its instruments, and the long history of its interaction with Earth, but without ongoing exchange. That silence is not failure. It is the natural close of a mission built around a finite energy reserve and extended by decades of careful stewardship. In another sense, Voyager 1's meaning does not diminish when its radio falls silent. The spacecraft carries the golden record, a phonograph record assembled as a symbolic message from Earth. It contains sounds, music, images encoded in analog form, and greetings in many languages. Scientifically, The record has no role in the continued operation of the spacecraft, and the chances that it will ever be found by another intelligence are unknown and likely extremely small. Yet its presence matters because it transforms the spacecraft from a probe of environments into a cultural artifact of departure. It says that the mission is not only about measurement, but also about representation. A small machine leaving the solar system carries with it a record of the world that made it, not because the galaxy demanded it, but because humanity chose to send one. This choice gives Voyager 1 a second identity. It is both an instrument and a sign. Even without the golden record, the spacecraft would symbolize technical endurance. With it, the mission also symbolizes self-description at the edge of the unknown. The larger legacy of Voyager 1 is therefore layered. Scientifically, it changes understanding of Jupiter-Saturn, the heliosphere, and the local interstellar medium. Technically, it demonstrates the power of precision communication, long-lived nuclear power, robust spacecraft design, and intergenerational engineering care. Historically, it connects eras. A craft designed with the tools and assumptions of the 1970s continues to operate in a world transformed by computers, politics, institutions, and generations of people. Symbolically, it extends the scale on which human presence can be said to exist. No human travels with Voyager 1, and no living being experiences its passage directly, yet it carries human intention farther than any earlier human-made object. That outward reach matters because it alters perspective. It makes Earth feel both smaller and more specific. The planet becomes the place that built a machine able to remain intelligible across interstellar distance. It becomes the source of the signal, the receiver of the whisper, the origin of the record, and the center from which all meaning in the mission has flowed. Voyager 1's final years, therefore, gather many themes into one quiet form. Weak signal fading power, patient repair, deep listening, cold endurance, and outward motion all converge in an ending that is not sudden but thinning. The spacecraft continues while enough energy remains to support order. When that order can no longer be powered, silence will arrive. Yet even then, the journey does not stop. Voyager 1 will continue around the center of the galaxy on timescales far beyond human planning, carrying inert systems and a cultural message through the dark. Its transmissions will cease, but its path will remain. In that way, the mission's last and most enduring meaning may be this: a machine can fall silent without losing significance. Voyager 1 will one day stop speaking to Earth, but it will still be a trace of Earth moving among the stars. A fading technical voice transformed into a lasting physical presence in the wider galaxy. The radio link grows quieter with time, but the meaning of the journey does not depend on endless transmission. Voyager 1 continues outward through the thin interstellar medium, moving under the same laws that carried it past Jupiter, past Saturn, and beyond the Sun's outer boundary. Its power declines. Its instruments fall silent one by one. Its systems, once busy with imaging measurement correction and response, narrow towards stillness. Yet the spacecraft remains what it has become over decades of travel. A small, durable object carrying evidence that a technological civilization once looked outward with patience and care. Long after the last command is sent and the last telemetry frame is received, Voyager 1 will continue on its path, no longer a working mission, but not an erased one. It will drift in darkness with its dish, its instruments, its generators, and its record of Earth, all preserved in the cold as motion continues. The vast distance between stars will remain almost empty, and the spacecraft will remain almost silent, but its existence will still mark a crossing from world to world, from the solar system into the wider galaxy. In that quiet continuation, the mission finds its calmest form. Not triumph, not loss, but persistence, carried beyond speech, where a human-made object keeps going through the dark, and the last whisper home gives way to a long and peaceful silence.